Hello. In this video today, what we're going to do is look at the geometric definition of an ellipse, followed by a derivation of an equation of an ellipse that's centered at the origin. So what is an ellipse, right? There's a couple ways to think about it. Probably the simplest way to understand it that anyone can understand, whether you know algebra or not, is geometrically, right? So imagine you take 2 points, just a piece of paper, put 2 points on it, maybe two thumbtacks in those 2 points, and we tie those 2 points together with this string here. That's the pink two lines, just one string, right? And maybe you put like a pencil here at this dot, right, to kind of pull that string taut. And you drag that pencil around on the paper, and as you trace it out, what it'll trace out is this special oval that we call an ellipse. All right, so geometrically, what that is, it is the set of all points in a plane, the sum of whose distances from two fixed points, which we call the foci, or focus for singular, is a constant. Okay, keywords here being that the sum of those two distances is constant. So this, right, because the string is a fixed length, right? So the D1 plus the D2, that's a fixed length, okay? All right, a couple of vocab words as we move forward. Every ellipse has a center we put right there at the middle. One side or one direction will be longer than the other, right? So this major axis, that's the distance, the furthest distance between 2 points on the ellipse. So the endpoints of that major axis we call vertices. So this is a vertex, that's a vertex. The other direction, the shorter side of it, we call that the minor axis, and those endpoints don't get a special name. All right, so just to help you visualize, right, here's a picture of kind of what that would look like if you took a pencil and you kind of traced it out. These two are placed rather far apart. So some foci are far apart. That makes it more elliptical. Or if you put your two thumbtacks or your foci closer together, you're going to get something nearly circular in shape. All right, so what we're going to do today is look at primarily where does this equation for an ellipse come from? Particularly, we're going to center it at the origin because that makes the algebra a lot easier. And it's really not that hard to just shift it once you have this equation. All right, so what we're going to do is place this on the origin. So we're going to call this point here, that's the origin 0, 0, if you want to label that. All right, so this here is a focus, that's the point C, and negative C. So that C is a positive number. So that is a distance to the right. Negative C then is negative. We're going to call A the endpoints of the major axis. Those are at your vertices. And then B here is the endpoints of the minor axis. That's just how we're going to name all of these points to make this thing work. So what we're going to do is to get the simplest formula for this, yeah, we're just going to use these points with C's and the origin at 0, 0. Okay. And we already talked about how this distance, I've called it H for hypotenuse, and I've drawn it here in such a way so that it's kind of it's equal, right? This distance equals that distance because you're going C to the right of the origin or C to the left of the origin. So that distance is also H right there, okay? So we got to do two things here, compute two different distances, and we're going to set them equal, right? So one of those distances that I want to look at is what if this random point is over here at A, right? A is a point on the ellipse. So therefore the distance from this focus to A, from there to there, that distance is a distance of C, the distance from here to the origin is C, plus A, the distance from the origin to there. So that distance is C plus A. And we know that that distance plus the distance from that vertice back over to the other focus, which is a distance, if you think about it, is A minus C, because the distance from the origin to there is A. Take away the distance from here to here, C, so we get that that distance is A minus C. We know that that distance is equal to, or that it's a constant. But first, let's go ahead and simplify, right? C plus A minus C. Your A's, we have two A's. A plus A makes 2A, and your C's cancel. Okay, we're going to also use this same diagram and apply the Pythagorean theorem to the triangles that I have shown right there, right? So by the Pythagorean theorem, okay, we have a little right triangle. Actually, we have two of them that are symmetric and equal, right? And so the leg squared, which is C plus the other leg squared, which is the distance from here to the top, that's b, so plus b squared, c squared plus b squared, is equal to what I'm calling h for the hypotenuse squared. So we can solve that for h by by taking the square root of both sides. We get the square root of, and I'm going to reverse that, just put them in alphabetical order there, b squared plus c squared is equal to the hypotenuse h. Okay, now we know that the sum of the distance from this focus to B, the negative C to B, and the B to that point, negative C there, is equal at any point on the ellipse, right, to the sum of the two distances. We found that at the vertex right here at A comma 0, that sum of those two distances is 2a, and I know that that has to equal the sum of h plus h, because by definition of an ellipse, geometrically, the sum of the distance from any focus to any point, from one focus to any point, and that point to the other focus is a constant. Therefore, the sum of these two distances, which is h plus h, has to equal to 2a, right? So I can set those equal. I can say, okay, so 2a has to then equal to 2h. And I can, well, divide both sides of that by 2 and then substitute in the value that we have for h. So dividing both sides by 2, and I'm going to switch to, I'll switch to white here, why not, right? So we get that a is equal to h, and h we just got is equal to the square root of b squared plus c squared. So this is a relationship between the foci, the vertices, and then this point B, which, doesn't get a special name on ellipses, but the length of half of the minor axis, I suppose, right? So what we're going to do just to simplify that, because we're going to come back to this and use it, is square both sides. So then we can say that, okay, a squared is equal to b squared plus c squared. You may see it in that form. Frequently, people solve this for c squared, and they write it as c squared is equal to a squared minus b squared. Okay, so that's a very special equation for ellipses relating the foci, the vertices, and the endpoints of the minor axis. Okay, and so we will revisit that later. Actually, when we do revisit it, it'll be in a slightly different form. It'll be, we're going to need to solve it for b, so let's go ahead and do that as well. If we solve this for b, we would get b squared, right, is equal to, if I subtract c squared from both sides, I would have a squared minus c squared. So that's just something I'll refer back to later in the derivation of this equation. Okay, so moving forward here, what we're going to do is let xy be any point on the ellipse, right? So it's just at a random place. It could be anywhere, okay? And I'm going to let my foci be at c comma 0 and negative c comma 0, okay? So then by the distance formula, let's apply the distance formula here for the distances between these two, the foci and the point xy, and the point xy and the other focus, okay? So by the distance formula, what can we say? Well, we can say that the sum of the distance from this focus to that point plus the sum of the distance from that point to that point is equal to 2a, because we already know that the sum, the distance, right, between the focus and any point, and that same point and the other focus can be reduced to 2a because it is a constant. So that is a very simple way to describe that distance. So therefore, we're going to say, okay, what is the distance from this first focus at negative c to a random point xy by the distance formula? Well, that distance would be, here, let's call it d1 here, and I'll call that d2. That distance would be, that's a 2, okay. There we go. D1 is equal to square root of, all right, it's the differences of the x coordinates. So I'm going to go right minus left here. So x minus negative c is going to simplify to x plus c squared, plus the differences in the y's would be y minus 0, which is just y squared. All right, and d2, that distance would be the square root of, let's see, the x minus c in this case. It's the difference between those two x coordinates. And then also it's the same on the y's, plus y minus 0. It's going to be y squared. All that's under the square root there. Okay. We know that the sum of those two distances, the d1 plus that d2, is going to equal to 2a. Okay, so what we're going to do is plug those in, the d1 and the d2 here in this equation. We're going to do some serious algebraic manipulation of this thing. All right, so plugging in d1, we're going to have square root of x plus c all squared plus y squared, plus that d2 is the square root of x minus c all squared plus y squared. We know that the sum of those two radicals is equal to 2a. And maybe I can center that a little bit better here. All right, so now, given that, what we're going to do is simplify this a lot. So to simplify, I want to square both sides, and it's going to be a lot easier if I move one radical to the other side. It really does not even matter which one, but I think I'll just subtract this one on the right from both sides to move it from the left to the right. So on the left side, I'm going to have really the same thing, square root of, and you can leave it like this, or you can multiply it out. Eventually, I'm going to have to multiply it out. So I'm going to go ahead and square out or FOIL out this x plus c all squared to get x squared plus 2c plus c squared. That's under the radical, along with this plus, oops, left off an x there, plus 2c times x. Let's go back and catch that. Plus 2c times x plus the c squared. There we go. And it is under the radical with that y squared right there. All right, that's equal to 2a minus this other radical, so square root of, and let's go ahead and FOIL that out as well, since we'll need to eventually. So that will be x squared minus 2 times c times x minus, no, plus the c squared plus that y squared, all of that is under that radical. There we go. All right. So now when we square both sides, it will eliminate one of those two radicals, okay? So squaring each side. So what you should do is pause this video and try this on your own. I'm going to assume you're comfortable with enough algebra for me to skip a few steps here, right? So if I square the entire left side, the square root is going to go away. That's going to be eliminated. And so we're going to get just x squared plus 2cx plus the c squared plus the y squared. Now, on the right, if we square that whole side, and maybe I should show that here, squaring that. If I square everything here, I'm really foiling out, right? Because we're gonna have 2a times 2a if I write this twice, right? And then 2a times this negative of that radical, plus another 2a times the negative of that radical, and then minus the radical squared, or the radical squared times the negative of the radical squared. Anyways, foiling it out. First we do 2a times 2a, so that gives us 4a squared. Then if I do the outside and the inside terms, well, outside and inside, you get the same thing each time. So if I do this times this plus this times this, I get negative 2a times the root minus 2a times the root is minus 4a times the root. Copy all that down. X squared minus 2cx plus c squared plus y squared. All right. And then the last term is plus, because we have two negatives, the radical times itself. And any radical times itself, the radical is eliminated. So we're left with x squared minus 2cx plus c squared plus y squared. Again, a lot of little bits of detailed algebra there, okay? Okay, from here, we do have several things that cancel out on both sides, right? So we have an x squared. If we subtract x squared from both sides, that's just going to go away. We can subtract c squared from both sides, and that's eliminated. And we can subtract y squared from both sides, and you can see it's going to get quite a bit simpler pretty quickly here. I'm looking at this. I've got a 2cx on the left and a negative 2cx on the right. So I'm going to add 2cx to both sides to get 4cx is equal to, okay, that one's now moved over here. So that's equal to 4a squared minus 4a times the radical. And it will continue to simplify down quite a bit. Now, whenever you solve radical equations that have two radicals in them, which is what the initial equation had, it had back up here, right? We had two radicals, one here and one here. And so the simplest way to do that is to put one radical on itself. That way, when you square both sides, one of your radicals is completely canceled. Then solve for the remaining radical and you repeat the process, okay? So we're going to somewhat isolate this radical. Everything does have a 4 in front of it, so we could just divide everything by 4, and that's going to clear out. All right, so what does that leave us with? And let's rearrange a little bit. I don't like this negative here, so I'm going to add that radical to both sides to get a times the square root of the x squared minus 2cx plus c squared plus y squared. All right, and that's going to be equal to, I'm solving for the radical. So I have this a squared already on the right. I'm going to put it over here. And then I'm going to minus that cx from the left, minus it from both sides to move from the left to the right. Okay, now I've got it down quite a bit. I think if we just go ahead and square both sides, I can leave the a there. There's no reason to introduce fractions. So we're going to square each side again. Square both sides again. And that will give us, let's see, I'll have this squared times the radical squared, so we'll have a squared times everything under that radical, x squared minus 2cx plus c squared plus y squared. All right, now if I square that, right, we're going to FOIL all of that. And again, maybe I should do what I did last time and kind of show, okay, what I'm doing is I'm squaring the entire side, show a little work, right? So if we FOIL that out, we'll have a squared times a squared, which is a to the fourth. A squared times negative cx plus a squared times negative cx is minus, let's go in alphabetical order. So 2 a squared cx followed by negative cx minus or times negative cx is positive c squared x squared. Okay, so we're getting there, we're getting there, we're getting there. Okay, so what we need to do is keep simplifying. If we distribute out this a squared over here on the left, okay, we're going to have a squared times x squared. Then a squared times negative 2cx would be minus 2a squared cx plus a squared times c squared plus last we'll have a squared times that y squared. And then on the right, I'm just going to kind of recopy what we have there. So a to the fourth minus 2a squared cx plus c squared x squared. And at least one thing cancels here, right? This negative 2a squared cx and negative 2a squared cx on both sides. If we just add that, it goes away. Okay, and this is really starting to clean up nicely. What we need to do is rearrange just a little bit. So I want to get all of the x squareds on the same side. And right now I've got this one over here on the right and this other one over here on the left. So I'm going to minus the c squared, a squared right here from both sides to move it over here to the left. So that'll give us a squared times x squared minus c squared times x squared. And then I'm going to bring down this plus the a squared y squared. I'm going to move that one to the other side. So plus a squared times y squared. And I'm going to subtract this one. So we have a to the fourth. I'm going to minus this term, a squared, c squared. All right, and the reason for that is I want to get all my x's and y's on the same side. And there's a nice little trick that's going to happen with the a squareds and the c squareds here, okay? So if I factor out this x squared from the first two terms, I'm left with a squared minus c squared. Recopy this plus a squared times y squared. And I can do the same thing on the right, factor an a squared out instead of an x squared, but that also leaves me with an a squared minus c squared, okay? See some patterns here, right? So then what we're going to do is we're going to divide both sides by the a squared times a squared minus c squared. Okay, we divide both sides of this equation by that, right? So what we have right here is, let's see, the a squared minus c squared will cancel with that one. So I'll have an x squared on top divided by an a squared on the bottom. So we'll have x squared over a squared. Right here, the a squared y squared divided by a squared times a squared minus c squared. The a squareds will cancel. So plus y squared over a squared minus c squared. And then on the right, everything cancels, so that is equal to 1. And what we did earlier was we derived how a squared minus c squared is actually just b squared. You might remember that at the beginning of this video. And that, my friends, is the equation of an ellipse centered at the origin in terms of A, which is the distance from the center to the end of the major axis, and B, the distance from the center to the minor axis. And there you have it.